is a proof for this. We will show that cardinality of positive rational numbers is less than equal to cardinality of natural numbers, and cardinality of natural numbers is less than equal to cardinality of positive rational numbers. These two together would imply that cardinality of positive rational numbers and natural numbers are equal. Why? Do you remember from last lecture? We saw this. It was called Schroeder-Bernstein theorem. And it was saying that if you have two sets, A and B, cardinality A is less than or equal to cardinality B, and cardinality B is less than or equal to cardinality A, then cardinality of A and B must be equal, right? So then Schroeder-Bernstein theorem would imply that cardinality of Q plus is equal to cardinality natural numbers. Okay, so it's only left to show these two. So let me call this one 1 and this one 2. So 2 is very easy. So first let's prove 2. To prove 2, how can I show that cardinality? How can I show that cardinality of some set A is less than or equal to cardinality of some set B? Do you remember from the definition? When can we say that cardinality of one set is less than or equal to cardinality of another set? If we can find or construct a one-to-one function from the first set to the second set. So if you don't remember this, please go back to the last time lectures. If I can construct a one-to-one function from first set to the second set, then I can say that the first set cardinality is less than or equal to second set cardinality. So we need to construct a one-to-one function as a f from n to q plus. If we show this, then according to the definition, we can say that cardinality n is less than or equal to cardinality q plus. And constructing a one-to-one function from n to q plus is extremely easy. What one-to-one function would you consider? So consider f from n to q plus, f of x equals x. Again, the identity function. Identity function, of course, is one-to-one, because f of a equals f of b, of course, implies a equals b, because f of x is equal to x. And it's a function from n to q plus, right? So f of 1, for example, is 1. The first element in the domain n is 1. F of 1 is 1, which is a positive rational number. F of 2 is 2, which is also a positive rational number, and so on. So f of x equals x is a function from n to q plus, and one-to-one function. So obviously, f is 1-to-1. Now to prove 1, consider, let's say G. Okay, 1 is what? I want to construct a one-to-one function from q plus to n, but I will not construct an explicit function from q plus to n, because it's hard to do that. A one-to-one function from n to q plus was easy, just identity function. But a one-to-one function from q plus to n would not be an easy job. I cannot consider identity function anymore, obviously, because for example, f of 2 over 3, if I define one to identity function, f of x equals x, f of 2 over 3 from q plus to n, f of 2 over 3 would be 2 over 3, right? But 2 over 3, 2 over 3 is not about 1. If I want to construct from q plus to n as an identity function, then f of 2 over 3 would be 2 over 3, and 2 over 3 is not in n, right? So that means I cannot consider an identity function as an option of a function from q plus to n. So what can I do? So it's a little bit tricky. I want to use step 1. Step 1 was saying that cardinality n is same as cardinality n cross n. So if I can construct a function from q plus to n cross n, then that means cardinality of q plus is less than or equal to cardinality n cross n, but cardinality n cross n we just showed in step 1 is same as cardinality n. Okay, so the trick is to use step 1 instead, because without step 1, the direct proof or direct construction of a one-to-one function from q plus to n, it would be very hard. So consider g from q plus to n cross n, and g of, let's say, m over n, I want to define it as m comma n. Okay, so every rational number is of the form m over n, and I'm defining that as m comma n. So let me say where m over n is the unique representation of a rational number where m and n have no common factor. It's important to mention this sentence. Why? Because, for example, let's say if I don't mention this, then I can write each rational number in many different ways, right? For example, 1 over 2 is same as 2 over 4, and this is same as 4 over 8, and so on. So if I work with this one, g of m over n, I define as m comma n. Then g of 1 over 2 would be 1 comma 2. If I work with this one, g of 1 over 2 would be 2 comma 4. If I work with this one, g of 1 over 2 would be 4 comma 8. So I will not have a function anymore, because for one input, 1 over 2, I will have multiple outputs. So in order to fix this issue, I'm saying that, okay, each rational number can be written as m over n, and make sure that m and n have no common factor. If they do, first simplify, right? For example, if you add 2 over 4, first simplify, get 1 over 2, then apply g to 1 over 2, and then g of 1 over 2 would be 1 comma 2. Or g of 3 over 8 would be 3 comma 8, because 3 and 8 have no common factor already. But g of, for example, I don't know, 4 over 16 would not be 4 comma 16, because 4 over 16 can be simplified. If it can be simplified, first simplify it. 4 over 16 is same as 1 over 4, and g of 1 over 4, then you can define as 1 comma 4. Okay, so that's a technical issue to be taken care of here. Now this g is 1-to-1. Why is it 1-to-1? So claim g is 1-to-1. How can I show it's 1-to-1? Well, I just need to show that if g of 2 inputs are equal, then the inputs are equal. So let's say G of M1 over N1 equals G of M2 over N2. Then according to the definition of G of M over N is M comma N. So G of M1 over N1 would be M1 comma N1. G of M2 over N2 would be M2 comma N2. And that means what? That means M1 is equal to M2 and N1 is equal to N2. If two pairs are equal, that's the definition of equality of two pairs, right? If two pairs are equal, the first coordinates are equal and the second coordinates are equal. M1 equals M2 and N1 equals N2. And that means M1 over N1 is equal to M2 over N2. Look at these two fractions. Their numerators are equal because M1 is equal to M2. Their denominators are also equal. So if you have two fractions, the tops are equal, bottoms are equal. And of course, the fractions are equal as well. So that means M1 over N1 is equal to M2 over N2. Well, that means G is 1 to 1. Right? I started with G of one input equals G of another input, and I showed that the first input must be equal to second input. Like G of A equals G of B, that implies A equals B. That means the function is 1 to 1. Now G is 1 to 1 means what? Hence, cardinality of Q plus is less than equal to cardinality of N cross N. I define the construct the one-to-one function from Q plus to N cross N. That means the cardinality of first set is less than equal to cardinality of second set according to the definition. By definition of cardinality A less than equal to cardinality B. Now, by step one, I know that cardinality N cross N is equal to cardinality N. So that means cardinality Q plus is less than equal to cardinality N. And that's exactly what I wanted to show, right? I was proving 1. And what was 1? 1 was cardinality Q plus less than equal to cardinality N. There you are. I showed this. We also showed that cardinality N less than equal to cardinality Q plus. And that means cardinality Q plus is same as cardinality N. So this was maybe the main step. Now step 3. Is the final result. Cardinality Q is equal to cardinality N, i.e. Q is a denumerable set. Okay, now proof of this. First, we will show that the set of negative rational numbers, so this means x such that x is less than 0 and x belongs to Q, is denumerable. In step 2, we showed that the set of positive rational numbers is denumerable. Now, in this step, we want to show that the set of negative rational numbers is denumerable. How can I show that? Well, that's very easy. We can easily construct a bijection from set of positive rational numbers to set of negative rational numbers. And if one of them is denumerable, the other one must be denumerable as well. So consider, let's say f from Q plus to Q minus, f of x equals minus x. F of x equals minus x. Okay, what type of function is this f? This f is obviously a bijection. So check It's very easy to check that f is bijection. 1-to-1 is very easy. F of a equals f of b means minus a equals minus b, and therefore a is equal to b. And is also onto, because every negative rational number is minus some positive rational number, can be written as minus of a positive rational number. Well, you just need to consider that positive rational number. Let's say if every negative rational number could be written as minus b, for example. Therefore, you just consider b itself. F of b is minus b. That means every element in codomain is in the range of the function. Therefore, f is onto. So I just told you how to check f is bijection, but please write the details. So what does that mean? F is a bijection from q plus to q minus. That means cardinality of q plus is equal to cardinality of q minus. The meaning of equality of cardinality of two sets. If you can find the bijection from one set to another, that means cardinality of those two sets are equal. And cardinality of q plus, we know it's same as cardinality n by step 2, right? And therefore this means cardinality q minus is same as cardinality n, and that means q minus is countable. Therefore, q equals q plus union q minus union 0 is also countable. Q, the set of rational numbers, can be of course written as set of positive rational numbers union set of negative rational numbers union 0. Q plus in step 2 we showed that it's countable. Q minus I just showed is countable, and 0 of course is countable. Countable, remember again, means what? Means either finite or denumerable. Q plus and Q minus are denumerable. 0 is of course finite. And union of countable sets. So here I have union of 3 countable sets. And by the property that we saw before, union of 3 countable sets is countable. And by property, I think I called it property 4. Property 4 above, union of countable sets union of, let's say, 2 countable sets is countable. This can be easily, this can be generalized. This can be generalized to union of 3 countable sets. Union of 2 countable sets we know is countable, but we can easily generalize it for 3 countable sets. How? Well, see, if you have 3 countable sets, let's say A union B union C, and you know that A, B, and C are countable. But by the property 4, we know that A union B is countable. You can call it D. And if D is countable, D union C will be countable, right? Therefore, this whole package will be countable as well. Once you know union of 2 countable sets is countable, you can easily generalize it to 3 countable sets. Again, how? You just need to consider A union B as one set, call it D. D is countable by the property 4. Then you have D union C. Again, you have 2 countable sets. Again, it's countable. Similarly, you can generalize it to 4 countable sets or 5 countable sets or n countable sets. So union of 3 countable sets is countable. And therefore here we have a union of the Q plus, union Q minus, union 0 is countable. So what does that mean? Let me just 3 countable sets. And here we have union of 3 countable sets, namely Q plus, Q minus, and 0. So Q is countable. So Q is denumerable, which is exactly what I wanted to show in this step. Here, Q is denumerable. If Q is countable, it has to be denumerable. Why? Because countable means either finite or denumerable. Of course, Q is not finite, therefore it's denumerable. Okay, so far we looked at some countable sets. Even surprisingly, Q is countable. We also looked at some properties of cardinality of 2 sets, but we haven't constructed an uncountable set yet. So next, we construct an uncountable set. So let's call it theorem. The interval 0 to 1 is uncountable. So we want to show that the interval 0 to 1 is uncountable. So the set of all rational numbers is countable, but the set of an interval, even if the interval is small, 0 to 1 is uncountable. How can I show that this is uncountable? So proof. Proof is by contradiction. In proof by contradiction, do you remember what we do? We have to assume what we want to show is wrong, right? So suppose that this interval 0 to 1 is countable. And then I want to reach a contradiction. So if a set is countable, again, countable means either finite or denumerable. Of course, the interval 0 to 1 is not finite, so then it has to be denumerable. Then 0 to 1 is denumerable. Denumerable. And what was the important feature of denumerable sets? The important feature of denumerable sets was that we can list the elements. We can list the elements as the first element, second element, third element, and so on. And hence, its elements can be listed. Say, for example, R1, the first element, I want to call it R1. Listing the elements means we can say which one is the first one element, which one is the second element, and so on. So first element, there exists a first element. So the first element, I want to call it R1. So what is R1? R1 is a number between 0 to 1, because remember, we are listing the elements in our set, which is open interval 0 to 1, as the first element, second element, and so on. So R1 is one of the elements between 0 to 1, one of the numbers between 0 to 1. So I can write it as, let's say, 0 point, let's say D1, D2, D3, and so on. R2, again, I can write it 0 point, or let me use this notation, D, let's say, 1, 1, D1, 2, D1, 3, and so on. So I have to use 2 indices. the first index, I have C Dij. The first index matches with the index of R. So if it's the first element R1, then I have D11, D12, D13, and so on. But so this index matches this index. But then I have, when I use the decimal expansion, I could have many elements after 0, right? So the first element, so the second index shows the position of D after decimal. So this is for the first number after decimal, second number after decimal, third number after decimal, and so on. So for the second number, again, as you can guess, the first index must match the index of R. So D21, D22, D23, and so on. That's the first index matches this again. First index again matches this, and so on. Second index again shows the position of the number after decimal. And so on. So you can say again R3 equals 0.D31, D32, D33, and so on. Okay. Okay, now here, these are the list of the numbers that I have, which are all between 0 to 1. And if my assumption is true that 0 to 1 is denumerable, every element in 0 to 1 must be listed here. So every element in 0 to 1 must be one of these Ri's. So if I can construct a number which is 0 to 1, which is none of these Ri's, then I will have my contradiction. Because remember, I was assuming that all the elements from 0 to 1 can be listed. Every number to 0 to 1 must be one of these Ri's. So now consider, let's say R equals 0. Or let's say C1, C2, C3, and so on, where now how can I define these CIs? C1 is equal to, okay, this is a little bit tricky, 2 if D11 is not equal to 2, and let's say 3 if D11 equals 2. Similarly, C2, again, is 2 if D22 not equal to 2 is 3 if D22 equals 3. Similarly, C3 equals 2 if D33 is not equal to 2 is 3 if D33 equals 2, and so on. So my claim is R is not equal to Ri for every I in N. So I have constructed a number R which belongs to 0 to 1, by the way. Why? Because it's 0 point something. 0 point. So first of all, 0 point, the first number after decimal is C1, and then C1 is either 2 or 3. That's the first number after decimal. Second number after decimal, again, is a number which is either 2 or 3. Third number after decimal is again either 2 or 3, and so on. So I have a number R where every number after decimal is either 2 or 3. Well, that means I have a number, of course, between 0 to 1. That's the first thing. And my claim is that this number is not any of these Ri's. If I show this, then that's my contradiction. Because I was assuming that every number in 0 to 1 is listed as one of these Ri's. So how can I show that R is not equal to Ri for every I? So to prove the claim, First, I want to show that R is not equal to R1. Why? What is R1? 0.D11, D12, D13, and so on. So I want to look at the D11. Now, if D11, let me give you an example. Let's say R1 equals, this is 0. For example, 5, 7, 8, 9. Now, this is my D11. Now, for C1, we said if D11 is not equal to 2, then let's define C1 to be 2. So then I would have for R, I would have 0.2 something, right? So therefore, R is not equal to R1. Because why? Because the first number after decimal for R1 is 5, but first number after decimal for R is 2. So of course they cannot be equal. So this is for in the case where the first number after decimal is not 2. But if it's 2, then the first number after R, after decimal for R, we define it as 3. And again, they will not be equal because this number is 2, this number will be 3. So we define C1 in a way that no matter what the first number after decimal for R1 is, the first number after decimal for R is different than the first number after decimal for R1. Therefore, R will not be equal to R1 because their first number after decimal are not equal. So I know it's a little bit, tricky and complicated idea, but if I want to simplify it, I want to show that R is not equal to Ri for every I. So first, let's see why R and R1 are not equal. R and R1 are not equal because their first number after decimal are not the same. If you have two numbers where their first number after decimal are not the same, then they cannot be equal. Because the first number after decimal for R and R1 are different. Why? Because if D11 is equal to 2, then C1 is not equal to 2 because C1 is equal to 3, right? If D11 equals 2, if D11 equals 2, C1 is 3, therefore it's not 2. And if D11 not equal to 2, then C1 equals 2. So regardless what D11 is, C1 and D11 are not the same. C1 is the first number after decimal for R. D11 is the first number after decimal for R1. So similarly, R and R2 are not equal. Similarly, R is not equal to R2. Why? I think you can guess now. R and R1 were not equal because their first number after decimal were different. Now R and R2 are not equal because their second number after decimal means their second digit after decimal are different. Again, similar argument, if D22 is equal to 2, then C2 is not equal to 2. Why? Because C2, if D22 is, sorry, here, if D22 equals 2. If D22 equals 2, then C2 is 3, and 3 is different than 2. That's what I said. And if D22 not equal to 2, then C2 is equal to 2, which again means C2 and D22 will be different. So continuing this process, R not equal to Ri for every I. So we found R between 0 to 1, which cannot be listed, or which is not listed as any of our i's above. And this is contradiction with our assumption. Our assumption was that every number between 0 to 1 is listed as one of these Ri's. But we found the number R, which is not any of these Ri's, and that is our contradiction. Okay, this argument or this proof was given by Cantor, who's a famous mathematician, and this argument is called Cantor diagonalization argument. So this method, this proof is called, or the method used, let's say this proof was given by Cantor, and the argument given above is called Cantor diagonalization argument. Cantor diagonalization argument, because we are looking at the diagonal elements, right? Remember, each Ri had many decimals in the decimal expansion, but when we wanted to construct the number R, we looked at diagonal elements. For C1, the first number after decimal for R, we looked at D11, which is the first diagonal element. Then for C2, we looked at D22, second diagonal element, then D33, third diagonal element, and so on. So that's one thing I wanted to mention. Also, some people here ask, how did we choose these 2 and 3? Well, the choice of 2 and 3 were arbitrary here. You could use any number 4 and 5, for example, or 4 and 7, 6 and 8, any two numbers. So the argument was, based on the fact that, okay, we have two possibilities for CI. The idea was to make sure CI and DII were different. So if DII not equal to some number, I said 2, then CI equals 2. If the DII equals 2, CI is equal to something other than 2. I said 3 here. You could say 4, as long as not equal to 2. And even this 2 here, as I said, is arbitrary. We could say D11, if D11 not equal to 4, then C1 equals 4. D11 equals 4, C1 equals 5, right? So these 2 and 3, my point is, can be replaced with any two other numbers. Okay, so that's another remark. And now the next theorem that I want to say, the set of real numbers R is also uncountable. How can you prove this? Again, by contradiction. Suppose that R is countable. Then 0 to 1, which is a subset of R, is also countable. Why is that? So this is, I think, one of the book exercises I included, I think, in the homework as well, that a subset of a countable set is always countable. A subset of, so check that a subset of a countable set is countable. If you have a set which is countable, any subset of it would be also countable. Now, if R is countable, 0 and 1, open interval 0 and 1, which is a subset of R, will be also countable. And this is contradiction with theorem above. Because in the previous theorem, we showed that the open interval 0 to 1 is uncountable. So if open interval 0 to 1 is uncountable, the set of real numbers will be also uncountable. Okay, so real numbers and open interval 0 to 1, 0 and 1 are both uncountable, which means that their cardinalities are bigger than the cardinality of natural numbers. But how about if I want to compare the cardinality of R and 0 and 1 with each other? I know that cardinality of R is bigger than cardinality of N, cardinality of 0 to 1 is bigger than cardinality of N. But what about R and 0 and 1 comparing with each other? Do you think R has bigger cardinality as 0 to 1? Or do you think the cardinalities are the same? The answer is their cardinalities are the same. So next theorem. Cardinality of R is equal to cardinality of, let's say, A and B, not only 0 and 1, any interval A and B. For any interval of the form A and B with A less than B. How can I prove this proof? So I want to prove this in 2 steps. Step 1, cardinality of R is equal to cardinality of minus pi over 2 to pi over 2. So minus pi over 2 and pi over 2 is one of the intervals of the form A and B. But why do you think I'm choosing this particular interval, minus pi over 2 to pi over 2? The answer is because for this particular interval, I am able to construct a bijection from minus pi over 2 to pi over 2 to all real numbers. So consider f from minus pi over 2 to pi over 2, minus pi over 2 and pi over 2 to R. F of x equals, what do you think the bijection would be? Tan x. Tan x. tan x is a function which is 1-to-1 on this interval. If I consider tan x on all real numbers, it won't be 1-to-1, but on this interval is 1-to-1 and is also on 2. So it's I can say it's a pre-calculus question exercise. So check f is a bijection. If I want to show you the graph, if you remember the graph from pre-calculus, it looks like this. You can draw it better. Okay, so as you can see from the graph, all the y values are covered. So the function is on 2, and also it passes horizontal line test, so it's 1-to-1 as well. But this is all just from the graph, it's not a proof. If you need a proof, you have to do it with the formula and the definition of 1-to-1 and on 2. But you can also do it that way. I left it as exercise, but I also gave you the intuitive reason that why this function is bijection, because the graph looks like this, and therefore every y value is covered, and also the graph passes horizontal line test. To check f is a bijection, this means that cardinality of real numbers is same as cardinality of the interval minus pi over 2 to pi over 2. This is minus pi over 2 here, by the way, and this is pi over 2. So this was step 1. And step 2, cardinality of, let's say A and B is same as cardinality of 0 and 1 for any interval of the form A and B with A less than B. So any two, this means any two interval have the same cardinality, any two interval of the form A and B, open interval A and B, because any two such intervals have same cardinality as intervals 0 to 1. Okay, let's see the proof. So again, I need to construct a bijection to consider f from 0 to 1 to A and B. F of x equals, so I want to construct a bijection from 0 to 1, 0 and 1 to A and B. So what happens if you want to go from 0 and 1? Let's look at the real line. Let's say this is 0 and 1. And let's say, for example, if I want to go to, let's say, 2 to 10. If I want to go from this set to this set, what type of operations do I need? So first of all, I need two types of operations, a shift and a scale. So the length of this interval is 1. The length of this interval is 8. So first of all, I have to multiply everything by 8. But if I just multiply by 8, 0 to 1 goes to 0 to 8, not 2 to 10. But once I have the right length, once I go from 0 to 1 to 0 to 8, right? So first I go to 0 to 8 by scale. And then I can go from 0 to 8 to 2 to 10, and I just need a shift. I just need to shift everything by 2. Right? So having this in mind, if I want to go from 0 to 1 to A and B, first of all, I have to multiply everything by the length of new interval, which is B minus A. And then shift it by a in order to go to a and b. So if I want to draw the right picture for this new scenario, see, we go from 0 to 1, 0 and 1, we scale it, and then we go to 0 to b minus a, and then if I add a to everything, then I go to a to b. So consider this. The claim is f is a bijection. So first of all, f is 1 to 1. This is very easy to check. Because if you have f of a equals f of b, or a and b are used here. Let me use different letters. Let's say f of x1 equals f of x2. Then that means that b minus a times x1 plus a equals b minus a times x2 plus a. That means b minus a times x1 equals b minus a times x2. And that means x1 equals x2. So this one was easy. And f is on 2. Why is f on 2? So I need to take an element in codomain. So take, let's say t belongs to a and b. And I want to show that this t, which is in codomain a and b, is f of some number in the domain which is 0 and 1. How can I find that number? Well, I want t to be f of some x, right? But let's solve for t equals f of x, and let's see what happens. So solve for t equals f of x. Then I'll get t equals b minus a times x plus a. So if I take a to that side, I'll get t minus a equals b minus a times x. And that gives me x equals t minus a divided by b minus a, which belongs to 0 and 1. I have to check that this x here that I find belongs to the domain. So if I can show that t in the codomain, any arbitrary t in the codomain is f of some element in the domain, then that means t is in the range, and therefore the function will be on 2. But if t is equal to f of something which is not in domain, then that's not useful for me. But this number here, t minus a over b minus a, is between 0 to 1. Why? Because t, where is t? T is between a to b. Look at here, I chose t between a to b. So t is between a to b. So that means t minus a is between 0 to b minus a. And therefore, t minus a over b minus a is between 0 to 1. Which is exactly what I needed. So that means t is equal to f of t minus a over b minus a, and therefore t belongs to range of f, and that means f is on 2. I took an arbitrary element in codomain and showed that that element is in range of the function. Therefore, my function is on 2. Okay, so we showed that interval 0 to 1 and interval a to b have the same cardinality. And what did I want to show originally? That cardinality R is equal to cardinality a and b for any interval a and b. So step 1, I showed that cardinality R equals cardinality minus pi over 2 to pi over 2. And then I showed that cardinality a and b and 0 and 1 are all the same. So if I combine these, what can I conclude? So combining step 1 and step 2, So cardinality R equals cardinality minus pi over 2 to pi over 2. This was step 1, right? But step 2 was saying that cardinality A and B for any A and B is same as cardinality 0 and 1. So this is same as cardinality 0 and 1 by step 2. And cardinality 0 and 1 again by step 2 is same as cardinality A and B for any A and B. So again, this one by step 2. Right? This is what step 2 was saying. Cardinality 0 and 1 and cardinality A and B are the same. So that means cardinality R equals cardinality A and B for any interval of the form A and B. Okay. So far we showed that we have, we introduced some sets which were countable and or denumerable, and their cardinalities were same as cardinality n. And we saw that some sets, for example, such as real numbers or intervals of the form A and B, have cardinality bigger than n. And they're uncountable and not denumerable. Now the question is there any set whose cardinality is bigger than n but less than r? So this is where a hypothesis called continuum hypothesis can be mentioned. See, we have shown that cardinality R is bigger than cardinality natural numbers, right? Now, is there a set A such that cardinality A is bigger than, is between these two basically? Cardinality A is bigger than cardinality natural numbers, but less than cardinality R. So let's compare this with numbers. If I have two numbers where one is bigger than the other one, for example, and 10 is bigger than 5, is there a number between these two? Meaning that a number which is bigger than 5 but less than 10. Well, for numbers, yes, of course. Now I can say 6, for example, bigger than 5, less than 10, or 6.1, bigger than 5, less than 10. But what about for the cardinalities? If I have two cardinalities where one is bigger than the other one, is there a set with the cardinality between these two? But the continuum hypothesis says no, there is no such set. So it's a hypothesis, as you can guess from the name, so it cannot be proved. But the hypothesis says that there is no such set. So the answer is no continuum hypothesis states that there is no such set A. So in the universe of cardinalities, in the universe of numbers, in the, for example, there are infinite numbers between 1 and 2. 2 is bigger than 1, and there are infinite numbers between which are bigger than 1, less than 2. But the universe of cardinalities of infinite sets, we have cardinality of natural numbers. Then we jump to cardinality of real numbers. So there are many sets whose cardinalities are the same as cardinality of natural numbers, such as integers or rational numbers. But if you want to have a set which with a bigger cardinality, then you have to jump to real numbers. Again, there are many sets with a cardinality of real numbers itself, or interval 0 to 1, any interval out there from A and B, and so on. But there is no set whose cardinality is bigger than n, less than r. Okay, guys, so this is a continuum hypothesis. And I think this much was enough about the cardinality of sets. And the next section in this chapter is about matrices. So 2.6 is about matrices. And we want to skip this because it will be covered in math 252, linear algebra. One of the main topics in a linear algebra course is matrices and their properties. So you will cover all the details in that course. So for this reason, we want to skip it in this course. And well, that's all then. This is chapter 2, and next time we will start. And chapter 3 we will also skip. Chapter 3 is algorithms. This one we will also skip. And chapter 4 is some basics of a number theory that we'll start next time. Okay, so thank you and see you on Thursday.